Imagine standing at the edge of a black hole, where Einstein's gravity says nothing dramatic happens at the horizon, yet quantum theory warns that information might be ripped from the universe. The firewall idea arrived like a lightning strike. At the boundary, a wall of extreme energy would scorch anything trying to fall in. If that were true, the gentle fall promised by the equivalence principle would break. But the real drama isn't a literal wall. It's a puzzle about entropy and information, how the universe can carry every detail of what fell in, while a black hole seems to radiate nothing but heat. Could the rule be simple and universal? Entropy encodes information, and Hawking radiation is its ledger, even if the pages are scrambled. The open loop is this: can a thermal glow really spell out a complete history? And if so, how would we ever read it? Before the 1970s, black holes were seen as perfect absorbers with no information leaking out. Then Jacob Bekenstein proposed that a black hole carries entropy, proportional to its surface area rather than its volume, hinting that it stores innumerable internal microstates behind a boundary. Stephen Hawking added a shocking twist. Quantum effects near the horizon cause the black hole to emit radiation. That radiation, he showed, is almost perfectly thermal, random quanta that carry no obvious trace of the matter that formed the hole. If you toss information into a hole, the outgoing radiation seems to erase it. The paradox was born. If the hole evaporates away, does the information vanish from the universe, violating quantum mechanics' rule of unitarity? The stage was set for a clash of principles, not just a clash of ideas. Then came the firewall debate in 2012, when Almhiri, Marolf, Polchinski, and Sully argued that to preserve unitarity, the early radiation must be entangled with the late radiation. But to preserve a smooth horizon, the exterior modes outside must be entangled with interior modes. You cannot have both. Many physicists treated that as a crisis in the very fabric of space-time. Others searched for escape routes: complementarity, fuzzballs, soft hair, and, most recently, holography and islands. This is the moment when the story shifted from a single paradox to a landscape of ideas about information, gravity, and how reality is stitched together. To understand how entropy might encode information, picture the black hole as a colossal quantum computer that scrambles data. The clue lies in entropy's area law. A surface can hide a vast number of microstates. In quantum terms, the information about what fell in doesn't vanish. It becomes entangled with every quantum of Hawking radiation that leaks out. If you wait long enough and collect enough radiation, you begin to glimpse the microstate map of the whole. Early radiation looks almost completely uninformative. Only after the page time does information start to leak out at a meaningful rate, turning the total entropy of the radiation up to a peak, and then, paradoxically, bringing it down as more information is revealed. That shape, the page curve, isn't a stubborn riddle, but a fingerprint of unitary evolution in a gravity-dominated quantum system. The moral is not that black holes forget, but that they encode memory in a highly scrambled form across many emitted quanta. The firewall argument sharpened this intuition into a concrete clash. Either information leaks out through subtle correlations across radiation, or the horizon preserves a perfectly smooth, drama-free crossing for infalling observers, but not both. The rescue plan, in the modern lexicon, involves a web of ideas about how space-time and information are braided. The holographic principle says the information content of a region can be described by data on its boundary, and the island formula provides a way to allocate quantum information between the black hole and the radiation so that unitarity is preserved without demanding a violent horizon. In practical terms, this means information isn't created in a final burst at the end. It's distributed through a network of entanglements that are reshaped by the very geometry of space-time. This is not simply a clever trick, but a deep shift. The behavior of entropy, the flow of information, and the fabric of space are all expressions of one underlying quantum information architecture. The story of how the information ledger is kept becomes a map of how gravity emerges from entanglement, and how a universe without loss might still hide its ledger behind a surface. These ideas ripple far beyond black holes. If space-time and gravity arise from patterns of quantum information, then the cosmos behaves much like a giant cosmic computer, with geometry acting as a code that keeps reality coherent. Black holes become laboratories where the rules of quantum computation, error correction, and information flow intersect with gravity. The notion of islands and replica wormholes hints that the fabric of reality may be emergent, not fundamental, and that why we experience locality could be a consequence of how information is redundantly stored and distributed across regions. This reimagines the holographic principle as more than a mathematical curiosity. It's a blueprint for how the universe protects and reveals information. The implications reach into how we understand quantum chaos, how we model strongly gravitating systems, and how we might eventually unify general relativity with quantum mechanics. It's a shift from asking what gravity does to asking what information makes gravity possible. Today, the paradox that once threatened to upend physics has become a springboard into a new paradigm. The firewall, once posed as a cliff, has yielded to a doorway into understanding how entropy encodes information, and how space-time might be woven from quantum data. The stubborn question, does information survive a black hole or vanish, is being answered not by burning the horizon, but by decoding the entanglement that binds every quantum to every other. If entropy is the voice of information, then the black hole is a choir whose notes are scattered across radiation in a way we are only now learning to listen to. If you want more mind-bending physics, hit subscribe now